Well, hello everyone, and today we will be solving one of the problem from LEED code. This is reorder list. It says you're given a head of a singly linked list. The list can be represented as 0, 1 up to many nodes till n minus 1 and n. So it is a list of n nodes, and we need to reorder the list in such a form that post 0th node there should be nth node, that is the last node. So post first node, the last first node, n minus 1th, 2, n minus 2, 3, n minus 3, and so on. So the example gives us a clear notation that post 1 we need to have 4, post 2 we need to have 3. And this is for even nodes list. What if the size of list is odd? Then in that case we need to take 3 as the ending character. With 1, we need to attach 5, 2, we need to attach 4, and 3 must be left as it is, with null as the next pointer. So it's pretty simple. Uh, the gist of a problem lies in this way, where you have a list. You can just break down the list in a form like just like this, and you can break the list in the form of 1, 2, along with 3 and 4. You very well know how to break the list within just one iteration within the middle. So I'm not getting details going in depth of it. If you still curious, I've made a video upon it. Click on the I button to know more how to break the list into two, or how to find the middle of a linked list. So similarly, if we have odd number of nodes, something like this, then we can break it down into like this, with 4 and 5 next. Now we have this list. Let's target on the even node first. We can do one thing, 1, 2. Here we have provided an operation of break, and now we'll provide an operation of reverse on the second portion, 4 and 3, reverse on second list, and in the end, we are very much merging the two linked lists. And it is something like 1, 4, then post it will go ahead with 2, 3. And this is our result. Similar to this, we will just iterate upon it, and we'll go ahead reverse this one. It will be like this, 5, 4, and the result would be 1, 5, 4, 1, 5, 2, 4, and 3. But how do we get to know the two ends of the list? So, so now we know the guess, we know the operations we need to perform. There are three operations. We need to break the list, reverse the list, and return the result. So without any further ado, let's break the list. But before breaking, let's handle the edge case, where head is null or head.next is null. It means head itself, the list itself is null, or it list contains only one element. In that case, we just return and we do not do any operations. But if that is not the case, it means list has more than one node, then let's find the middle. You know how to find the middle, and I'll not get into technicalities and details of it. I'll just show you this is the way to find middle, where after this loop ends, the slow pointer would give you the middle of a linked list. Now we have fast pointer, we have slow pointer. How do we know where to break it? Because in this case, 3 would be the slow pointer, and in the example 2, again 3 would be the slow pointer. But notice here 3 within the even list is the start of the second list. But here 3 is the end of the first list. How do we come to know about it? So there's a pretty well problem upon it. It's a very good problem, and we can handle it very well by checking the fast. So if fast is equal to null, in such case 3 is the start of the list. Else if fast is not equal to null, then 3 is the end of the first list. Keeping that in mind, let's create two variables for storing list1 and list2. So list1 would always be having the head node as head, and we are not sure of list2, so for now I have just created it, assigned it to slow pointer. If you want, you can treat it as null as well. So it's not a big deal. But what we have to check is whether the fast is not equal to null or is equal to null. So we need to have two cases if fast might be equal to null or not. So if it was not null, then you know though, then you do know that here the list2 begins with a slow.next. In this case, slow.next is the new list in such a way. But if it is null, then list2 is equal to slow pointer. And we also need to this part, and we also need to point 2 to the end because 2 we need to separate it out. So what do we do? 2 arrow next is equal to null. The next of 2 should be null. So we have stored 2 within the previous pointer. Let's use the previous pointer. In this way we broke the linking from 2 and 3 as in this example. Now things are pretty much simpler. What we want to do is the next part is to reverse the second list. So we have completed this. So let's mark it completed. Let's reverse this. So now things are pretty simple. List 2 is equal to reverse list 2. So I'm reversing the list 2 and I'm storing it to itself. Now we need to write down the reverse method. If you do not know how to write down the reverse method, I do have a separate video upon it. I'll also link that video within the I button. You can go ahead, click on it. You'll get a very detailed analysis on how do we reverse, what is the reversing mechanisms, and there's no need to memorize this reversing algorithm. You will get a thorough idea of what it. For now, without wasting any of the time, I will write down the best and optimal way to reverse a linked list. So this is a reversing of linked list. It works upon O of 1 space complexity and O of n time complexity. So now we have reversed it. We need to just merge the two lists. So list 1 and list 2. That's the only case now. So to merge this reverse list, I have created a new method. So let's go ahead and code it out again. So I'll just do private void as it's not returning anything and merge. I'll take list node. Let's not bother about it. And it goes like this. So I have a node A, B. I have assigned a dummy node just for iteration. I have used a iterator variable and then I go ahead with the iteration of A and B. So initially I assign A to the iterators next. I advance the A. I advance the iterator. Then I assign B to the next. I advance B and I advance the iterator. It's all. It might be a case where both lists are not equal. In that case, list A is for sure greater size is of greater size, and hence we can check if A is still not equal to null, we assign A to the next of iterator and just advance the A. Well, it's not necessary, but still let be. Let's remove that. And in this way, we merge two lists. If you wanted to know how to merge a linked list, uh, or rather, for that fact, how to merge a two sorted linked list, you'll get a detailed idea within the I button above. I highly insist to go ahead watch it so that not only you will get a thorough understanding how to merge two linked lists, but you'll get a very deeper understanding how to merge a two sorted linked list. Now things look very clear. Let's try to run this code so that our code is working fine. It compiles well with the existing test cases. Yeah, it works well, and let's submit it. So cool. It seems the rest of test cases has been worked as well. So this was an iterative approach where we have iterated over the list and we have made three operations. There are multiple ways you can do these operations. I still do not encourage you to rely upon the stats provided over here, but the time complexity. Here, the time complexity of this algorithm goes, let me quote it down. Here, the time complexity of algorithm goes within O of n, and space complexity goes O of 1. Because we do not use any of the space here, and everything is happening iteratively. Neither the stack space is being used. Uh, Whereas if you can see the code which has beaten this problem, it has used a stack space, and that's the reason it has a time complexity of O of n because it uses internal stacks. And yeah, it seems fast upon CPU, but it is because the CPU architecture is being made in such a way. But that's one of the beautiful reason not to rely much upon the time or execution time, but to rely upon time complexities. That's the reason why they are made up. So this was about me explaining how to reorder the linked list. If you like this video, then show your love down below. Until next time.
Myself, oh no, you will never forget me. Oh